Hey guys, welcome to the first video of this video series, and here we are to discuss the module 4 of our GTV1 course, and the module 1 discusses about consolidation. So let us start. Now from our classes in college we discussed a term called compressibility. So if you remember, compressibility is nothing but the decrease in volume of a soil mass when a load is applied over it. Okay. And we also discussed that compressibility is of two types. One is compaction, where there is expulsion of air from the voids of the soil, and the other is consolidation, where there is expulsion of water from the voids of the soil. Compaction on one hand is a very instantaneous process, that is, it occurs in a very small amount of time, whereas consolidation is a time dependent process. That means it takes a lot of time to take place. All right. Now, before we discuss the concept of consolidation, let us first try to understand some of the factors that affect compressibility. Okay. The first factor is soil type. Now you know that soil is broadly classified as coarse grain soil and fine grain soil. So first let us see the effect of coarse grain soil on compressibility. Suppose I have got a soil mass. Okay, I have got a soil mass in a beaker and I apply some load over the soil mass. See, P is the load that is I am applying over the soil mass. So what will happen? The soil particles, they will come close to one another, right? And when they will come close to one another, the voids or void ratio among the soil particles will decrease. So one thing that I have established is with the increase in loading or with the increase in stress, void ratio decreases. Okay, so now let us see the first curve over here. Here what I have done, I have taken void ratio. Okay, I have taken void ratio on y-axis and effective stress on x-axis. All right, and if you see, the effective stress is increasing from 0, 20, 40, 60, 80, 100. It is increasing, and the void ratio here I have decreased from 0.75 to 0.50. So the curve that I am obtaining is somewhat like this, which is sloping downwards. Okay, so this curve is actually for loose sand. Okay, and this is for the dense sand. Okay, so you can see that for loose sand, this is the range for which it is getting compressed. Okay, so the void ratio for which the soil is getting compressed is from 0.75 to 0.50. So the range of void ratio for which loose sand is getting compressed is very less. All right, now compared to dense sand, the compression of loose sand is more. Actually, dense sand is far less compressible. You can see that the slope of dense sand is far less when compared to loose sand. So the major conclusion from this curve is that with the increase in loading, compression decreases. Okay, and the compression of coarse grain soil is less. Okay, the void ratio for which it is getting compressed is very less. Now let's move on to the second curve. Okay, so in the second curve, if you see, I have got compression in terms of percentage, okay, and time in minutes on the x-axis. So you can see compression is from 0, it is increasing, and finally I have got 100% of compression. So as soon as I applied load in a coarse grain soil, compression that is taking place in a very less amount of time. Okay, you can see within 4 to 5 minutes, 100% of compression is attained. Okay, so in a coarse grain soil, compression occurs almost instantaneously. Okay, it takes place in a very small interval of time. So this was the case of coarse grain soil. Let us now see the case of fine grain soil. So the same curves I have taken, now just in place of coarse grain soil I have got fine grain soil. So in the first curve I have got void ratio and effective stress on the x-axis. So now you can see that the void ratio has got a wider range, right? it is extending from 1.20 to 0.20. And this is the reason that I have written that decrease in void ratio is large when compared to sand or coarse grain soil. Okay, fine grain soil undergoes a larger compression when compared to coarse grain soil. Now why it is so? It is because if you remember from the class of permeability, that is K for fine grain soil is very less as compared to K of coarse grain soil. So the compressibility or consolidation of fine grain soil will be taking a huge amount of time, and hence the range of void ratio is also very high. Now if you see the second plot, that is between compression and time, fine grain soil takes a lot of time. Okay, to achieve 100% of compression, it is taking almost a time of 10 to the power 4 minutes, which is far higher than what we have seen in coarse grain soil. So that is what I have written. Compression continues for a longer amount of time in case of fine grain soil. All right. So this is the first factor that is affecting compressibility, that is type of soil. Let us look at this second factor, that is stress history. So stress history means what kind of stress the soil was subjected to in its past. Okay, in very simple words, if I say, it is the history of stress of a soil. Now before we discuss anything, stress history gives rise to three types of soils. Okay, one is normally consolidated soil, abbreviated as NC soil. Second is pre-consolidated soil, or sometimes called over-consolidated soil, abbreviated as OC soil. And the last is under-consolidated soil, or UC soil. Let me explain the OC soil first. Okay, so suppose I have got a soil. Okay, I have got soil mass, and there is a rock over it, a huge rock, which is applying a load of say 1000 kilonewton over the soil. Okay, so because of this rock, the soil particles will now be getting compressed, right? Now someone decides to build a building over the same soil mass. So what he does, he demolishes the rock, okay, and now he constructs a building over the same soil mass. Now the stress or load that the building is applying over the soil is say 500 kilonewton. The rock was applying 1000 kilonewton, and the building is applying a load of say 500 kilonewton. So obviously now the soil is subjected to a lesser amount of stress compared to its past. Okay, so such kind of condition gives rise to over consolidated soil, or OC soil. That means a soil is said to be over consolidated if its previous pressure was higher than the present pressure. Okay, if the previous effective stress, to be more precise, was higher than the present effective stress, then that type of soil is known as over consolidated soil, or OC soil. Now what about NC soil? So let me take the same example. Let me take the same soil mass, but this time there is no rock. Okay, the soil mass is barren. Okay, there is no structure over it, and now someone decides to construct a building over the soil. So now he constructs the building, and this building applies a load of 500 kilonewton per meter square. Okay, so this is the stress that the building is applying over the soil mass. So now the soil is subjected to a stress for the first time in its life, right? Because earlier the soil was barren, there was no structure, or there was no load over it. So the soil in which the previous effective stress is equal to the present effective stress is known as NC soil. Or to be more simple, if I say, NC soil is that soil which experiences the stress for the first time. All right. And finally I have got under consolidated soil. So under consolidated soil means a soil which is undergoing consolidation. It is still under the process of consolidation. Okay, it is not fully consolidated. So such kind of soil is known as under consolidated soil or UC soil. Okay. Now, if you have understood the three types of soil, we can move to a concept called over consolidation ratio or OCR. So what is OCR? OCR is nothing but it is the ratio of pre-consolidation stress divided by present consolidation stress. Pre-consolidation stress means the stress prior to compressibility or prior to the consolidation. So in the OC soil where there was the rock, this rock was actually the pre-consolidation stress. Okay. And present consolidation stress for that soil will be the building. Okay. So in case of an OC soil, OCR will be always greater than 1. Why? Because pre-consolidation stress is always larger than the present consolidation stress, which is quite evident from the example. If you see, the rock was actually applying a stress of 1000 kilonewton per meter square. So this becomes the pre-consolidation pressure or pre-consolidation stress. And now the building is applying a load of 500 kilonewton per meter square. So this is the present consolidation stress. So 1000 divided by 500 will give you OCR of 2 kilonewton per meter square, which is, sorry, 2, it should be 2. So OCR will be larger than 1. Now, in case of NC soil, OCR is always equal to 1. Why? Because if you take the example of the barren land, pre-consolidation stress, what was the previous stress? Previous stress is equal to the present stress. I have told you that in an NC soil, pre-consolidation stress is equal to present consolidation stress. So pre-consolidation stress will be 500 and present consolidation stress will be also again 500. So 500 by 500 will give you OCR equal to 1. Alright. And in under consolidated soil, the present consolidation stress will be larger than the pre-consolidation stress. So OCR will come out to be less than 1. Okay. So this is how stress history plays an important role in compressibility. Now let us see a curve. Okay. So this curve is between void ratio and effective stress. Okay. But effective stress is plotted in a logarithmic scale. So this is actually a semi-log graph where E is along y-axis and log sigma dash or effective stress is along x-axis. So now observe very carefully. So what I'm doing is I'm applying some load or I'm applying stress, I'm increasing stress. So from this point to point A, you see the soil is getting compressed. Okay, but the amount of compression is not very high. The slope of the line is very less, right? The decrease in void ratio is also very less. So that means that this up to this region, up to this stress, okay, up to this stress, let's say sigma 1, up to sigma 1, the soil is actually an over consolidated soil. That means it is already subjected to a stress of sigma 1 in its past, and that is why now it is not compressing at a very high rate, it is compressing at a very low rate. Okay, because already it has been subjected to a stress of sigma 1. Now if I increase the stress beyond sigma 1, the soil will be subjected to the stresses beyond sigma 1 for the first time in its life, right? And if a soil is exposed to a kind of stress for the first time in its life, it acts like an NC soil, right? So from point A to point B, the soil will now be acting like a NC soil, and so you can see that the decrease in void ratio is very, very high. Okay, you have got a very steep slope over here. So earlier this slope or this line, it was not having a very high slope, it was getting recompressed. Okay, so hence it is termed as recompression. And after that, after point A, this soil is getting compressed for the first time in its life, right? So this is a virgin compression. For the first time in its life, it is getting compressed for this amount of stress. So after point B, after reaching point B, what I decide is I decide to leave the load. Okay, I decide to release the load. Now as soon as I release the load, the soil does not bounce back to the original position. Okay, this is because soil is not a fully elastic material, it is an elastoplastic material. So instead of going back to its original position, or to position say A or somewhere over here, it goes back to a position say C. Okay, so as soon as I lift the load, the soil particles will now move away from one another, and hence I have got some amount of expansion over here. Okay, but the important point is the soil will not bounce back to its original position, rather it will be going and occupying a different position, which is termed as point C. So once it reaches point C, again I begin to apply load. Okay, so if I begin to apply load, the decrease in void ratio will not be again a steep one, because from this stress the soil is already being subjected to in its earlier stage, right? So now again the soil will be behaving as an OC soil, right, till this point D. Okay, up to point D the soil has already been stressed, so the decrease in void ratio will not be that much, and hence I have got again a case of recompression. After point D the stress will be again a new one, and now the soil will be behaving again like a normally consolidated soil, and again I will be having a very steep slope after point D. So this is the entire curve that is explaining the concepts of OC soil and NC soil. Now from this curve, if I magnify the region of DE, okay, if I see the line DE, it is a straight line which is sloping downwards, and the soil here is behaving like a NC soil. So this is what I have drawn over here. Okay, this is point D, this is point E, and from D to E I have got a straight line. Void ratio is decreasing say from E1 to E2, and stress is increasing from say sigma 1 dash to sigma 2 dash. Now if I try to find the slope of this line DE, it will be E1 minus E2 divided by log sigma 1 dash minus log sigma 2 dash. So this slope is termed as compression index. Okay, compression index, it is termed as CC. And what is CC? CC is nothing but slope of this line DE. So if I write the slope of this line, it will be E1 minus E2 divided by log sigma 2 dash minus log sigma 1 dash. So if the change in void ratio E1 minus E2 is written as delta E, and log sigma 2 dash minus log sigma 1 dash is written as log sigma 2 dash by sigma 1 dash, this gives you the term of compression index. So compression index tells us the extent to which a soil is actually getting compressed. But the most important thing that you should know is compression index is only and only applicable for an NC soil. It is only applicable for NC soil, because from point D to point E, the soil was behaving like an NC soil. For the first time in its life, it was subjected to a stress beyond point D. So it was behaving like a NC soil. So that is the concept, that compression index is only applicable for NC soil, right? And after that, the last factor that is important is effective stress. Okay, so here is a plot between void ratio and effective stress. In this case, I am taking a normal scale. Okay, this is not a logarithmic scale. So if you see, if I am increasing the stress, void ratio is getting decreased. Now observe carefully. Suppose initially I had a void ratio E naught. Okay, and then I apply some load, or you can say I am increasing the stress by del sigma dash. Okay, I am increasing the stress by del sigma dash. So now from E naught, the void ratio decreases to E1, right? It decreases to E1. After E1, what I do, I again increase the stress by the same amount, that is I increase it by del sigma dash only. So now the void ratio will decrease from E1 to E2, but you can see that the decrease from E0 to E1 and the decrease from E1 to E2 are different. Okay, the decrease from E0 to E1 was higher, whereas the decrease from E1 to E2 is a bit less. So if I denote the decrease from E0 to E1 as del E1 and the decrease from E1 to E2 as del E2, then you can say that del E1 is actually greater than del E2. So what I can conclude from this curve is, for the same increment of effective stress, that is I have increased the effective stress by the same amount, del sigma dash, the change in void ratio decreases. Okay, firstly, for the first time it decreased by an amount of del E1, but for the second case it decreased by an amount of del E2. So the change of void ratio decreases for the same amount of increment of effective stress. Now for this curve, if I try to calculate the slope, then the slope of this line is termed as coefficient of compressibility, which is denoted by AV. Okay, and what will be the slope of this line? It will be del E. Del E means decrease in void ratio divided by del sigma dash. What is del sigma dash? It is the increase in effective stress. So del E by del sigma dash gives you coefficient of compressibility. And I have also put a negative sign over here, which indicates that void ratio or the change in void ratio decreases with the increase in effective stress. So negative sign signifies that del E decreases with the increase in effective stress. Okay, so these were the factors that affect compressibility. So we will continue with the other topics in our next video. Okay, thank you.